If you look at figure 826, you got your feeder, this is your feeder, and you got capacitors here, capacitor here, right? It's not every single node. It's not every single node. Why? Because you need to look at cost. You cannot come up with a solution that I'm going to put, you know, a Ferrari to every employee, right, as a gift, right, for Christmas, right? That doesn't make sense, right? So you have to look at the cost of what you do. And so what's happened here is that I start with, this is basically the current profile, right, from the substation, right, that block there is the substation. You start with I1, and then as basically current is uniformly distributed, right, means all the loads draw the same current, so basically you, and if you can assume that is, in reality it has to be little blocks like that, right, that will be the current without any capacitor. And here is the equation with X, which is assuming to have that and not, you know, little things that go back like that, is you are assuming that all this is uniformly distributed as a function of X, where X is the length of the feeder. Now, if you put capacitors here, right, the current that I need, so here at the end, right, I start with I2, right, that's the load required, and coming here, right, well, at this point, the current is dropping because the capacitor here is providing part of that I2, right? So that's the current. And then when you come here, right, you start providing all the loads here. At this point, further reduction of the current because you have now this capacitor providing some current. And then you keep going. So this is what the source is providing, right? That's basically is the increased capacity is that now instead of the source producing this, is delivering this current, I can use the difference, right, to sell it to somebody else, right, on another feeder. Okay, what about if I decide to put a capacitor bank on every single node? So how many capacitor banks do I have there? 2. Okay? Here, I have 3. And so you are going to have the same graph, right? And here I have 4, right? 1, 2, 3, 4. And then you can see that you start having all these little things. Well, let's keep putting forever, right? We are rich. Well, and under this assumption, this is the graph. So what's happened when n is equal to 1? Right? This is the power per unit loss reduction. And this is the total reactive compensation level. What is 1? 100%. Right, look at that. The per unit loss reduction basically is about when we have 60%, right, of compensation. Now, you have 1 capacitor bank. If I put 2, right, I can get a better per unit. What is the base power for this? Per unit loss reduction. Okay, if it's per unit, I need to have base power, right? You know, it's Thursday, 2:06, too many questions, right? The brain is saying lunch, lunch, lunch. Well, if it were the power of the transformer, right, what's happened? You got a 1 per unit there. What is 1 per unit? 100%. Means that 100% of the power on the transformer is dissipating in losses? Cannot be. Doesn't make sense, right? So what else? There is some case without capacitors that is assumed as the base case. So the losses at that base case are 100%. Those are my base power for this calculation, right? And so, right, this is 10% of the power under the case with no capacitors, right? So the case with no capacitor represents your base case. And so that's where all these pages are. They are basically telling you, I have a distributed energy, uniformly distributed load, and I'm adding capacitor banks. So if I go from 1 to 2, I have an improvement. What about the improvement for 3? Right? It's not that big. But you just bought another transformer bank. Capacitor bank. Right? What about if I put infinite? Right? I have a uniformly distributed load. I put infinite capacitor bank. Look at that. From 3 to infinite, you don't get anything. So what is the moral of the story? You see that this calculation is good. It's not practical. Sorry, it's practical in a sense that I will say just now. Right, I don't like it because because it creates, there is a method there how to place the capacitors that we have used. One of my graduate students doing energy storage has used some of these ideas for placing energy storage when you are trying to compensate for the variability of the PV arrays. If you think you have a distributed generation, means solar panels, right, and those, as the sun, right, goes behind a cloud changes, you need to have some energy storage to take care of the variability. Well, so we use some of these ideas, right? The problem with this is, like, for example, the optimum value is 2/3, right? You know, they calculate all these distances, which are fine if you have a uniformly distributed load. But the good things about that is that this exercise, which is theoretical in nature, allows you to draw conclusions. This is the important thing. It allows you to draw conclusions. So what is the conclusion that you draw from that picture, that graph? That obviously infinite is not a solution. Having a capacitor bank next to every single node in the homework is not a solution. And I think that I even wrote it there because in case that someone said, well, I put capacitor banks. But it's not a solution for 2 reasons. Number one, technical, right? You don't get much benefit. And number 2 is economically. You are spending money that really doesn't buy you anything, right? So that's the reason why this figure is important. Here they are doing another type of comparison, and it's the same story. Look at that. So when you have a feeder, you will have a tough problem putting more than 2 capacitor banks. With 2 capacitor banks, you should get a lot of benefit. Adding a third one, don't expect to have a very large benefit. So even that the whole analysis uses a theoretical ideal feeder, we can draw conclusions that we can generalize. So, you know, they keep doing and all this. Let me talk a little bit about, so